Welcome friends, welcome you all in my channel Chemistry and History of Molecules. I am Tanmay. So today I shall discuss a very important point, nucleophilicity versus basicity. Often students get confused whether the reaction will be nucleophilic or basic. Actually these two are two different topics into different domain, but often we confused. So I shall try to give a clarity about nucleophilicity and basicity, mainly focusing on their differences. Okay, and this is a continuation lecture of substitution reaction. So I suggest you please see those videos first. After that you come to this, it will be beneficial for your understanding. Okay, so generally means first reaction is that Rx plus Nu. What happens? Attacks. It could be SN1 or could be SN2, depending on the nature of the substrate and nature of the nucleophile. Okay. Second, so if we compare this versus this, you can see here that plus charge and minus charge combine to produce a neutral species. So from common sense, it looks like that, okay, this reaction will be faster, but there are some differences that we'll discuss today. Actually, nucleophilicity is a carbon center fact. Okay, carbon center, and carbon is not highly electropositive, not highly electronegative. So it's a relatively less electronegative compared to nitrogen, oxygen, fluorine, etc. atom. So electronegativity less means easily polarizable. Easily polarizable. What do I mean? Means the electron density on carbon could easily be dragged or modified using some external factor. So what does it mean? That they easily oxidized. So what does this factor indicates? The electron cloud is in soft in nature. So if it is soft, so it could give electron to softer, means not only carbon, other soft electron this center could attack easily to form such type of reaction. Okay, so soft in nature. So these are the criteria for a good nucleophile. Okay. So these are the criteria, that easily polarizable, easy to oxidize, soft in nature. So this thing is there. So in the opposite side, actually acidity is associated with the hardness of a molecule. So hard center is needed, means electron density higher, is difficult to polarize and difficult to oxidize. Means they have a very high electron density over them. So they will prefer to give their electron to the hard center, that is the proton. So actually this is the typical definition of basicity. But if we look closely, actually basicity means this nucleophilicity versus basicity. If we compare, this basicity is proton based and nucleophilicity is carbon based, and nucleophilicity, this is a kinetic. Nucleophilicity is a kinetic phenomenon. And basicity is a thermodynamic phenomenon. Okay. So friends, today this lecture may be little long, but for complete understanding, I shall keep all the points in the same video. So I suggest you please look the video completely. Okay. Okay. So this is the basic factors about nucleophilicity and basicity. So now we are going to explain few points which will give you a clear idea. So if we consider same center, means two atoms having common center, but one is charged versus one is uncharged. For example, this, okay, let's write the reaction. Rx plus Nu equal to Rnu. So, this OH minus versus H2O. So, if we compare their nucleophilicity versus basicity, this is a stronger base. This is weaker, but here the nucleophilicity and basicity is same. Why? So if this reacts with Rx, here everything is same, but another thing here, charge density is more. So we can think like that, this reactant's energy is higher. Intermediate almost similar, so reactant energy is higher. Okay, that's why they are more reacting. And second, that actually reaction is happening, this electron is going to this center to this. So if they have more electron for attack, then attack will be favored. Okay, so this is the factor charge. Again, if we think if we consider everything based on charge, then the basicity will be reflected to their nucleophilicity. What do I mean? This ethoxide anion, phenoxide anion, acetate anion, and nitrate anion. Okay, this. So here the basicity is less in this side, basicity is more in this side. Okay, so this side basicity increases, this side nucleophilicity increases, because here the charge density is more, because only ethyl group, no conjugation. Here there is a conjugation with this phenyl ring. Here equivalent resonance structure possible here, and this is also like that. So in this way basicity will be similar to their reactivity. Now if the charge factor is also same, then what adjacent atom, for example HO minus 0.3, so HO minus versus HOO minus, so we should write in this way, it's better, minus. Here this lone pair repulsion makes it more active, means increases the ground state energy. So actually today we are mainly discussing about this substitution on sp3 center. Okay, and actually the reality is the effect of this alpha effect on this nucleophilic reactivity is less in case of sp3, more in case of sp2. So we will discuss this factor in the next video, where I shall explain exclusively about this alpha effect on nucleophilic attack. Okay, so here the nucleophilicity will be more as the ground state energy higher, but difference is very low compared to this versus this. Okay, okay. So third point. So the fourth point is, if the charge also similar but hybridization difficult. The fourth point is hybridization. What do I mean? For example, sodium hydride versus sodium borohydride. So this hydride is having this, actually both produces H minus. Okay, here the H minus is the electron is in s orbital, so which is purely symmetrical, spherically symmetrical. So but here this is sp3, so this hydride is attached to a sp3. So what happened, what do I mean? This in this way, and it is sp3, and actually hydride is taking this bond pair to attack someone. So this, it has more nucleophilicity because of directional character of this sp3 orbital. Okay, so here the point is about the directional property. Okay. Now the next point is along a group, what happens? Along a group means, for example, if we take nitrogen, oxygen, phosphorus, sulfur, in this way if we go down, okay, what will happen? So let's take about the example of oxygen. For example, RO minus versus RS minus. What happens? In case of oxygen, it is 2p. In case of sulfur, it is 3p. Sorry, third row element, it is second row element. It is third row element. So what happens in this case? So this is sulfur is larger in size. Sulfur is larger in size. So the electron density on this sulfur is less compared to oxygen. Okay, and both have a negative charge. Okay, fine. Another thing, size is big and it has same amount of charge. So charge will be more diffused. So the size will further enhance due to the negative charge. So it is easily polarizable. Okay, and since it has electron on this this sulfur is a third row element, so its energy is relatively higher ground state. So if we consider a particular reaction, then intermediate energy is almost closer, but ground state energy different. So this energy of activation will be less in case of this energy of activation of sulfur will be less in case of this sulfur thing. So reaction rate is expected to be higher. The similar phenomena is observed in case of amine versus phosphine. Okay, so this is more nucleophilic compared to, because this is phosphorus is soft centered due to this bulk size. So similarly, if we check another thing like this fluorine, chlorine, bromine, iodine, the same phenomena observed. Fluorine sometimes shows some complex behavior. That's why I am not considering this. Fluorine will be a special example. But if we check about the chloride, bromide versus iodide, what happens? We know iodide bromide is a very good leaving group because the negative charge is on a bigger, means chlorine it is a third, it is a fourth, it is a fifth row element. Okay, so what happens? This charge is localized over a big space, soft, easily polarizable, so they have a very high nucleophilicity. But reverse, if we think, very less basicity. So basicity is in this order, nucleophilicity means basicity is this order, and nucleophilicity is this order. Okay, similar thing, this basicity is in this order, nucleophilicity is in this order. Okay, okay. So we have discussed about simple nucleophiles for these substitution reactions. Okay, so right now we will discuss about embedded nucleophiles. Okay, embedded nucleophiles, what do I mean? Embedded nucleophile means they have two centers for attack. For example, cyanide. Okay, cyanide. So cyanide, this, or even nitrite, NO2 minus. Okay, so if we compare electronegativity of carbon versus nitrogen, then nitrogen is more electronegative, so electron density is higher. But here some different property observed, because it can attack using this side or this side. Here also one pair, and here is one bond pair that eliminates to form this negative charge. So two electron. Even in case of nitrogen, here is one pair, and attack can possible from oxygen side also, because here three lone pairs. So example, if we take alkyl halide plus potassium cyanide in alcohol, product is RCN. Okay, instead of that, if we take silver cyanide, what is the product? The product is RNC. Actually this is plus, this is minus. This is called isocyanide. Okay, the question is why this difference happens. Why this difference happens? This difference happens because of the nature of the transition state. Means here if we consider this Rx, this X is slightly more electronegative, so this is slightly high, so this follows an SN2 type pathway. Okay, so this is, so cyanide attacks from back side and it eliminates. Fine. So another, it eliminates to produce RCN, and this charge is not that much significantly higher. It's normal, like the electronegativity of this. So carbon attacks. But in contrary, if we discuss about the Rx plus silver, and this X is equal to halide. So what happens? This silver cyanide, we know silver plus has an affinity for alkyl group, halides. So what happens? It produces a RXAG type. So previously it was delta negative. Right now, after donation, coordination, these eggs became delta positive type. Okay, and silver became negative type. And this consequently means after this donation, this slight positive increase in positive charge pulls this electron density from this to this more, and even make it more positive charge. So if it is more positive, means this is a harder center. Harder means more means charge density is very high. That time instead of this carbon, it prefers to attack using this, and this attack results in this RNC formation. Another explanation is there, but that explanation is actually this bonding between silver and carbon is similarly covalent type. Okay, fine. So when this silver is bind to this halide, because silver has an affinity of halide, then this cyanide is also attached here. So the free carbon, availability of free carbon nucleophile in the reaction medium is less because this bond is little covalent character. So we can expect another molecule of cyanide having this nitrogen lone pair can attack this to produce that alkyl nitride. This isocyanate. So this is the explanation. So another another factor is that nitride. Let me explain. The story is similar. For example, if we take sodium nitride versus silver nitride. When we add sodium nitride, then simple like sodium cyanide or potassium cyanide, this reaction happens, attack happens on this side. Okay, but when alkyl silver nitride is added, silver forms this complex, and consequently due to this formation, the carbon centers become harder, more charged. That's why this oxygen attacks to produce that RON. Okay, and proof here, sodium nitride produces NO2. Okay, so nitride, and this is oxynitride. So what's proof of this? If you reduce this with lithium aluminium hydride, it produces amine. But if you reduce this, it will produce alcohol. And additionally, this ammonia, or means it will produce ammonia or hydroxylamine depending on the reaction condition. Okay, so this plus this, so this will be, so here one product is amine, another is alcohol. This is the proof of this concept. Okay. So till now we have learned about the nucleophilicity versus basicity. Okay, so one thing I want to mention along with this, that nucleophilicity is a very important factor because it controls the nature of the substitution reaction. What I am saying? For example, if this nucleophile is strong enough, so it may control the reaction from SN1 to SN2. Why? Because in SN2 reaction, you can see in the RD step, in the RDS, both nucleophile and the starting are involved. Okay? But if the nucleophile is not strong enough, then this reaction will become SN1 type reaction, where only substrate, concentration of substrate is responsible in the rate determining step. So it is very important to have a good nucleophile for this reaction. So another, I forgot to mention another type of nucleophile which we observe, that is azide. It's a very important nucleophile because of its needle shape. So this is not a bulky, but needle shape, and both sides it can attack. So reaction rate is also expected to be higher. And another thing, this excellent nucleophilicity results a new strategy for reaction, that is nucleophilic catalyst. What does it mean? What does it mean? Means that, for example, if you have a nucleophile here and this nucleophile is not good enough, then what people does, they add some good nucleophile like Ki. What happens? These iodide first react with Rx to produce and Rx to produce Ri, and we know iodine is a good living group, so iodide attacks it. And another thing, iodide is good nucleophile, and another thing, iodide is a good living group also. So what happens? This nucleophile Nu attacks this R to produce. So overall, what does this nucleophilic catalyst? It reduces the energy of activation. For example, previously this looks like this. So this is the intermediate. Okay? And this is the product, this is the reactant. Right now it reduces, it reacting this way to produce this. For example, this is the nucleophilic catalyst intermediate. This is the intermediate formed after the reaction, that is this Ri. This Ri is here. So overall, if we consider the energy of activation, this decreases a lot, and consequently rate of reaction increases. So this is the importance of nucleophilicity. So I guess nucleophilicity. So this is the end of the video. In next video, I shall explain the nucleophilic attack on unsaturated compound, mainly carbonyl compound. That is a very important thing. So if you like my teaching, please give a like and subscribe my channel Chemistry, the Mystery of Molecule, and press the bell icon to get the notification of every single video I upload. And finally, share this video among your friends such that many people could be benefited from my info. So see you in my next video.